In 1905, Albert Einstein, who was a graduate student at the time, proposed a new, very radical theory. A number of recent studies had come to understand a little bit more about light and the principles of light, but they showed some really interesting phenomena that happen when you get close to the speed of light. Albert Einstein proposed this new theory, and this theory said that the laws of physics depend on the reference frame from which they are measured. By reference frame, we mean point of view. Let's look at an example to describe reference frame. Let's say that we have a car traveling from the right at a rate of 30 miles an hour. You're standing off by the side of the road, the car passes you at 30 miles an hour, end of story, nothing fancy about that. But if you also see a police car traveling from the left at 50 miles an hour, well, you've got two cars going those speeds. Now let's say that you are the policeman sitting in the car. From your point of view, the red car isn't coming at you at 30 miles an hour, but coming at you at 80 miles an hour. So we say that the red car's speed is 80 miles an hour relative to the policeman. So this measurement is relative to the reference frame, and so this is the dawn of Einstein's special theory of relativity, saying the laws of physics are relative to the reference frame. Einstein's special theory of relativity comes up with a very interesting result. What it shows is that time actually passes differently for objects traveling close to the speed of light than they do for objects not traveling that fast. Here's the basis of this theory. Einstein reasoned two principles. One is called the consistent law principle, and the other the constancy of speed principle. The consistent law principle states that the laws of physics remain the same if you are in the same reference frame as some occurrence. For instance, you're on a starship traveling close to the speed of light. Since you're in the starship, you watch an object fall, it follows the same laws of physics we've seen and we've studied in this course. But if you were to watch that happen from the Earth as the starship passes close to the speed of light, you're in a different reference frame, the physics actually changes a little bit. That's what we mean by the consistent law principle. Now, the constancy of speed principle states that speed of light, independent of the reference frame, travels at a rate of 300 million meters every second. That speed of light is constant. It will not change. And Einstein showed through calculations that this really is true. Okay, let's do a very simple demonstration that shows how important the special theory of relativity is. Let's say that we have two objects traveling close to each other, very similar to the two cars we saw in the last slide. The one from the left, object A, we'll say, is traveling at 150 million meters per second, and the object from the right, we'll say object B, is traveling at 200 million meters per second. And this is what you see. But if we do the same math we did for the cars, then from the perspective of object A, object B is traveling at a speed of 350 million meters per second. Now there's a problem here. Remember that the speed of light is 300 million meters per second? Well, it turns out that nothing can go faster than the speed of light. And so using basic laws of physics, we break a fundamental principle. And all of a sudden, physics just doesn't work anymore. So there's something else that needs to be explained. And this is where Einstein's theory of relativity comes in. Basically, what the special theory of relativity comes out to show us is that measurements are different when taken from different moving reference frames, especially at speeds close to the speed of light. The measurements that change are that the length of an object is shorter when it's traveling, when it's moving. The clocks run more slowly when they start to move. And moving objects have more mass. These are three very big and important results of the special theory of relativity. Relativity effects are quite negligible at normal speeds, at speeds that you and I travel around. They happen, but they're so negligible that we just don't account for it. But when you get close to the speed of light, these relativity effects become extremely important. One very classic example of this is a satellite. As a satellite travels around the Earth, it's traveling at extremely high speeds, not the speed of light, but much faster than you and I are moving. As such, relativity does become slightly important, quite important actually. And there's one particular satellite that affects you very much, and that is the GPS. GPS systems have to take into account the special theory of relativity to give you correct measurements. So with the development of Einstein's special theory of relativity, we see that not only is space a variable, for instance, the east-west, north-south, up-down dimensions, not only are those variables, but now time is a variable as well. The special theory of relativity says that there are variations in space and time. So Einstein continued on this thought and developed what we now call the general theory of relativity. To demonstrate the general theory of relativity, what I have here is a fabric. Often we talk about a space as being the fabric of space and time. This is probably one of the reasons why, because this is a good analogy. The difference is that the fabric of space and time, all of space, is 4 dimensions: up and down, north, south, east, west, and time. But we can't really demonstrate that very well here, so we're going to use a 2-dimensional sheet to try and to demonstrate this a little bit better. Say you have a flat sheet, and then you have a mass. Take the mass and put it on the sheet. What's going to happen? It's going to create a little divot, kind of a compression here in the sheet. Now, you can't see it as well with a small mass, but if you have a larger mass, the divot becomes much larger. There's kind of a compression in the sheet around here. Now, here's the really cool thing. If you have two different masses, let me make this one a little bit larger, then you have 2 divots that are going to start interacting with each other. Now, let's go on a smaller scale first. Let's say that we have, say, a very large mass in the middle, so a very large divot created by, I don't know, maybe a star. And then a small marble. This small marble may be, say, a planet. If I let go of this planet, what's it going to do with this divot? It is attracted and will sink into the bottom of this divot. It is attracted to the mass in the middle. Now, if I do this just right, it's a little more challenging to do, but if I do this just right, I can actually, there's a little bit, you can actually get this marble to orbit. There's a little bit, just almost had it there. We can see how objects orbit around. Yeah, it's a hard one to get. But you can see how the planet, the marbles, curve around the larger mass. So Einstein's general theory of relativity describes more than just more weird stuff that happens with time and space. It's actually the most accurate description we have now of gravity, what causes gravity. Now, just for fun, we're going to put on our 2 masses again. Let's add a little bit more mass over here and have, say, a binary star system. What would happen to a planet? I haven't done this, so this is totally new and untried. Let's see if we can get it to work. What would happen if I send a planet right through the middle of these? That was probably a little too hard. But you see that it's kind of fighting between the two. It's attracted to both masses. And so it kind of changes the gravitational pattern. If this were a perfect sheet, what I would see is I would see it orbit one and come around and perhaps a perfect figure eight pattern. If I could get it just right, but that takes a lot of skill, which I'm not very skilled. That's okay. So that is the whole idea of the general theory of relativity and the fabric of space and time.